China has revealed a breakthrough that could reshape the entire future of satellite technology. Engineers at DFH Satellite Co, led by Su Zhenhua, created a prototype power system delivering 2.6 megawatts with 0.63 microsecond precision, a level of control never achieved in an orbit-ready design. This leap could transform communication, propulsion, and sensing in space. In this episode, we uncover how it works, why it matters, and what comes next. China's new satellite power architecture stands out because it solves a challenge that once looked impossible, combining extremely high power output with extremely accurate timing in a system compact enough for orbital use. The DFH team achieved 2.6 megawatts of pulse power, a level far above the sub-megawatt performance typical of earlier technologies. At the same time, the system coordinates 36 power modules with a timing deviation of only 0.63 microseconds, a massive improvement over earlier systems that often struggled to synchronize within a full millisecond. This improvement is rooted in three key engineering decisions. First, the system uses large solar arrays or similar high-capacity power sources to collect energy continuously. Solar power is abundant in orbit, but using it for intense bursts requires careful conversion. Second, the incoming energy passes through high-efficiency DC-DC converters, shaping it so it can be cleanly stored in compact, pulse-ready components. Third, the stored energy is released through a controller built around an FPGA, field programmable gate array. FPGAs are ideal for fast electronic coordination, and here they manage the precise timing of all 36 modules. Together, these components form a synchronized energy burst engine capable of delivering short, powerful pulses without destabilizing the spacecraft. Unlike older systems limited to slow, steady output, this design intentionally uses microsecond bursts because they deliver high energy without requiring enormous continuous power sources. The prototype results were obtained in ground tests, but the architecture is explicitly designed for satellites. It is scalable, modular, and flexible, allowing engineers to design specialized versions for different missions. What makes this so important is simple. Satellites have never had access to this much controlled power before. This opens the door to a new class of orbital capabilities. Once a satellite gains access to megawatt-level bursts with microsecond accuracy, its potential applications expand dramatically. One of the most talked about possibilities is high-power laser communication, a technology that transfers data using narrow beams of light. These systems already promise speeds far beyond traditional radio communication, but they are limited by the power of the beam and the precision of the signal. A satellite powered by this new architecture could send much stronger optical pulses and maintain cleaner timing, improving both range and data capacity. Another major area is advanced propulsion. Spacecraft powered by ion thrusters often operate at low power for long periods, slowly but efficiently adjusting orbit. With access to short bursts of intense energy, a spacecraft could accelerate more aggressively when needed, then revert to efficient mode once the maneuver is complete. This hybrid approach could support rapid orbit changes, faster travel between orbital layers, and improved mission responsiveness. The system also offers new opportunities in space-based radar and high-resolution sensing. Many remote sensing platforms rely on short, powerful pulses of radio waves, microwaves, or laser light. Stronger pulses lead to clearer images, longer ranges, and more advanced scanning modes. Precision timing improves signal coherence, which directly boosts imaging quality. Finally, this architecture supports dual-use infrastructure. The same power system could enhance scientific research, Earth observation, environmental monitoring, and space weather instruments. Engineers could even use high-power pulses to calibrate sensors or support experimental physics missions in orbit. This shift from steady power to controllable bursts marks a major step toward more adaptable, multi-role satellites, platforms capable of switching between communication, sensing, and maneuvering in real time. Although the prototype demonstrates impressive capability, several major engineering challenges stand between laboratory success and orbital deployment. The first is thermal management. Any system releasing megawatt-class pulses must manage waste heat, and satellites cannot rely on convection like devices on Earth. Instead, spacecraft use radiators that expel heat slowly into space. Engineers will need to design lightweight, efficient radiator systems that can handle rapid temperature swings from high-energy discharges. The second challenge is power generation and storage. Solar arrays in orbit degrade over time as they face radiation and micrometeoroid impacts. Producing enough energy to repeatedly charge large capacitor banks demands robust arrays and high-capacity buses. Meanwhile, energy storage components must withstand constant charging and discharging without losing performance. The mass of these components must also be kept low enough for launch. A third factor is orbital environment durability. Radiation is a constant challenge in space. Electronics, especially high-voltage components, must be shielded without adding unnecessary mass. The system also requires strict electrical insulation to prevent arcing, especially during high-energy discharges. Precision timing introduces further complexity. The controller must keep the 36 modules synchronized despite vibration, temperature fluctuations, and long-term electronic drift. FPGAs can manage this on Earth, but verifying stable performance in space will require dedicated orbital testing. Operational transparency will also be important. Because the technology supports many peaceful uses, communication, propulsion, sensing, responsible disclosure of platform capabilities will help maintain global trust and prevent misunderstandings. In short, China's prototype shows that the technical pathway is real, but bringing it to orbit requires progress in cooling, storage, shielding, and long-term reliability. The direction is set, but the engineering journey has just begun. China's new prototype marks a turning point for satellite engineering. By delivering 2.6 megawatts of pulsed energy with 0.63 microsecond precision, the team at DFH Satellite Co has demonstrated a capability that could change how satellites communicate, maneuver, and sense the world around them. The architecture is modular, adaptable, and designed for future mission flexibility. Challenges remain, including heat control, energy storage, radiation protection, and long-term stability, but the potential impact is hard to ignore. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries, and don't forget to leave a comment below. Thank you for watching, and see you next time.